The binomial distribution. How likely are two or more defects in a fixed inspection batch? The binomial distribution models the number of successes in a fixed number of trials when every trial has two defined outcomes, the same success probability, and independence under the study design. Its parameters are the trial count n and success probability p. Use the Explorer to inspect exact masses and cumulative probabilities for counts. Do not apply it to an unconstrained event stream or to trials whose probabilities change materially. The mass at k combines n choose k possible success sequences with the probability of one sequence, p to the k times 1 minus p to the n minus k. This reasoning depends on exchangeable trials with a common p. The combinatorial coefficient alone does not create a binomial process. The distribution is symmetric only when p equals 0.5. For p below 1/2, it is typically right-skewed. And for p above 1/2, it is left-skewed. As n grows, while expected successes and failures are both comfortably large, a continuity-corrected normal approximation can be useful, but the Explorer computes the binomial model directly. A PMF bar reports the probability of one exact count, so its height can be read directly as px equals k. The CDF at k adds the masses from 0 through k. Because the distribution is discrete, the CDF changes in steps rather than along a smooth curve. A line historically produces a defective unit with probability p equals 0.04 under stable conditions. An inspector selects n equals 25 units using a design that makes the Bernoulli approximation reasonable, and asks for the probability of observing at least two defective units in the batch. Define x as the number of defective units among the 25 inspected items, so x follows binomial 250.04. The required event is px greater than or equal to 2, which is easiest to compute as 1 minus px less than or equal to 1. Use the CDF at k equals 1 or add the exact masses for 0 and 1 defect. Px equals 0 equals 0.96 to the power of 25 and p. X equals 1 equals 25 0.040.96 to the power of 24. Their sum is about 0.736, leaving an upper probability of about 0.264. Check the expected count n times p equals 1. And expected non-defects n times 1 minus p equals 24. Because expected successes are small, a symmetric normal approximation would be poor. The exact discrete calculation is the more appropriate result here. If the historical p equals 0.0, 4 model and trial assumptions hold. Batches with 2 or more defective units occur about 26% of the time. That rate is not sufficiently rare by itself to establish a process shift. A monitoring rule should be designed in advance and account for repeated batches, sampling dependence, and the cost of false alarms. Try it free at distriscope.com.